Welcome to our final Zoom lecture for the semester. And of course, we're saving the biggest for the last. We are going to be looking at the sun. Don't look directly at the sun. Of course, it is raining outside as I'm looking outside my window today, so how appropriate. The sun is the biggest and most powerful thing in our solar system, except for the occasional little cloud that gets in the way. It's somewhat ironic like that. But even with all of the clouds and rain, it is still an 85-degree day here as I'm doing this video, which tells you the sun is pretty powerful, even if it's being blocked a little bit by the rain and the clouds that are out there. We're going to look at the sun. We're going to look at the different aspects of the sun. And of course, the sun is 99.9% of everything in our solar system. So in many ways, when we think about where we live in the solar system, we have the sun plus a little bit of debris off to the side. And the Earth is actually only a small fraction of that debris, because most of that debris off to the side is in Jupiter and Saturn. So the sun counts for a lot. We would not be here without the sun. We would not have life on this planet without the energy that is created on the sun. We need the sun in many, many, many different ways. So without any further ado, let me give you the sun. Oh, that's over here. Okay. Yes. Let me start sharing my screen one final time, and we'll figure out what's going on here. The sun has been shining for a long time. Our current projections tell us it's been shining with a fusion reactor burning inside for a little over 4.6 billion years. We suspect that it will last for another 7 billion years or so, given the trajectory of how stars that are the same size as our sun work out in the rest of the universe. We compare our sun to different stars that are out there, and that gives us an indication of what we're dealing with. But our sun can be looked at in different ways. We can look at it in X-rays, we can look at it in ultraviolet, we can look at it in infrared, we can look at it in radio waves. The sun puts out energy in all of these different parts of the electromagnetic spectrum. So sometimes you'll see pictures like this, which will be bringing the sun to you in a way that you're not used to seeing. But the sun has been a mystery for a very long time. We've been looking at it for all of human history, and sometimes cultures have worshipped it. The sun god Ra, for example, in Egypt is perhaps the best known example, but that's far from the only one. And of course, it dominates the day, and it is very apparent, even if you're not scientifically literate, that it is very important. So there's been a lot of speculation. What is happening on the sun? And ironically, for as long as we've been looking at it, we've only really known for about 100 years what's happening inside. For the longest time, people have thought it was on fire. It might even be Apollo's chariot wheel sort of going across the sky on fire. But the thing is, we know what fire is. And fire is a chemical process. We can burn paper, we can burn coal, we can burn gas, we can burn any number of things. But the thing is, when we do that, we can take a reading of how much heat is coming off, how much light is coming off. We'll call that luminosity. And when we measure how much stuff is coming off of the sun versus how much stuff would need to be burned to get that, we come up with the sun lasting about 10,000 years. Now, if you're a young Earth creationist and think the world's only 6,000 years old, then you might not have a problem with that number, except here's the thing. That would be more than halfway through the life cycle of the sun. Again, what's the problem? The problem is ash. When you burn something in a chemical process, there are things left over. So more than half of the sun would be burned up now, and we would have a big pile of ash somewhere, probably on the sun. We're not seeing that when we look there. So it has to be something other than fire. Now, in the 19th century, in the 1800s, people were addressing this problem seriously, and they came up with another solution. Is it contracting? Is it compressing? Is it somehow under its own gravitational weight creating heat inside? And with that, we call that gravitational potential. And that gravitational potential versus, again, the amount of energy that's coming off of the sun would give us somewhat around 25 million years. That's a little bit better in terms of we're not looking for quite so much ash. But at the same time as people were thinking about this with regard to the sun, people were also looking at rocks and looking at our planet and looking at things in a geological sense and figuring out that the planet seemed to be a lot older than that. 25 million years won't even get us back to Jurassic Park, much less to many, many, many of the other much earlier supercontinents on the planet. Geological estimates of our planet were going from 100 million years to 500 million years to 1 billion years. It kept getting longer and longer as our techniques improved. So this was sort of on the way, but not quite there in terms of what the sun is. So we had to say no to that. It wasn't until Einstein came along, and the key dates here are 1905 and 1915. That's when he did his theories of relativity, and there are actually two of them, a special one and a general one. And the famous equation E equals mc squared comes out of that relativity process. Now, what this means is this is a very simple equation. E is energy, m is mass or matter that we've got in ourselves, that we've got in the planet, that we've got in the sun. And c, if you remember from when we were talking about earlier in physics, is the speed of light. So if we're talking about the speed of light, remember it's 186,000 miles per second. It's 300,000 kilometers per second. When we're dealing with this equation, we actually put it in meters, so it's even more. But that's squared, so that's going to be 300,000 times 300,000 if we're dealing with kilometers. We're dealing with 300 million times 300 million since we're dealing with meters. That's a huge number, which means you only need a tiny amount of matter to get a lot of energy. When we put that together with the amount of energy that's coming off the sun, that gives us a lifespan for the sun of around 10 billion years. That seems to fit, because here's the other thing. Again, I talked about ash before. In this process, as we'll see here shortly, you take particles that are hydrogen, slam them together, and that fusion process creates helium left over. When we look at the sun, we see the helium content growing and growing and growing. That's what's happening inside the sun. Now, the sun is in fact gas, but gas sort of weighs down on itself like anything. If you have a ton of feathers at the bottom of all the feathers, even though each individual feather is going to be light, you're going to have, your scale is going to register a ton. If you have a ton of pillows, well, if you have a ton of gas, that's going to press down further and further and further. I can't imagine being the guy on the bottom here of our display. But that's what's happening on the sun. And as gravity pulls the material inside, the energy from the center is pushing outward. So we end up in what's called gravitational equilibrium. The sun is pushing out with its engine, it's pushing in with gravity, and it reaches something called hydrostatic equilibrium. Now, hydro usually implies liquid, but it's the same kind of process that's happening here. Pressure is pushing inside, and or outside from the energy. Pressure from gravity is pushing inside. So we have a balance. But the sun actually does pulse a tiny bit because of this, and we'll see how it does that here in just a moment. The energy balance actually does change over time. The sun is brightening a tiny bit over time, and it will continue to do so. And of course, as we're doing that over millions and billions of years, it does turn into a significant addition. Venus, which is hot and too close to the sun, may have been in the habitable zone many billions of years ago, before the sun was as bright as it is today. The Earth is probably not in any danger of not being in the habitable zone before the sun just finally runs out of fuel. But Mars may actually become more and more centered into the habitable zone as the sun brightens. And now this is a very far off future I'm talking about here. I'm not talking about next 100 years or next 1,000 years. I'm talking about 500 million years from now, along the way for that. But our sun, as it uses up the material to generate the energy actually does become lighter and lighter along the way. But again, that the sun is so massive, it's almost imperceptible, certainly within the span of any human lifetime, certainly within the span really of the entire human race. The sun hasn't lost even 0.1% of its mass in terms of how much it's burned along the way. The sun has a structure that is complex, but pretty easy to understand. We have here on our picture here, here's the Earth. You can barely see it up against the sun here. The sun is 300,000 times as massive as the Earth, which means if this were divided into Earth-sized chunks, there would be 300,000 of them. But this is squeezed into a sort of volume here where our radius is going to be 109 Earths. So you could stretch a little over 200 Earths all the way across the sun here along the way. And in terms of its luminosity, how much energy it's putting out, think about a light bulb. Typical light bulb is going to be 60 watts, 100 watts. If you have a bright light bulb, it's 200 watts. This is 3.8 times 10 to the 26th watts. That's a huge amount. Think about it, 3.8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. Oh, see, hey, we even went beyond there along the way. This is a huge number. We're talking, if we were to put our little commas in there, there's our millions, there's our billions, there's our trillions, there's our quadrillions, there's our quintillions, and we're getting up to numbers that we don't even typically use. Now remember also, our typical light bulb is like this. So, and we should actually put it way over here, oh, so that it actually makes sense. To sort of see how much the sun is putting out. To put it in a relative term, the sun is putting out so much energy that every second, because watt is how joules per second, how much energy is coming out per second. It puts out more energy per second than the entire human race has ever used in its entire history. So we're not going to be in any danger of running out of solar energy anytime soon. Now, on the absolute top surface, we have an atmosphere of the sun. The sun is actually generating energy, but it's also pouring off particles. Those particles that are coming out into the solar system, we call the solar wind. Doesn't operate quite the way our atmospheric wind does, but it does actually percolate out, and we have solar wind particles that reach all the way out beyond Neptune. We've been able to measure solar particles all the way out there, and they will interact with our atmosphere. They'll interact with different things in the solar system, but it is very light. If I had an empty box, there would be more particles of air in that empty box than there would be particles of solar wind out in space. In fact, if I were to empty out and turn that box into a vacuum, as good as a vacuum as I could get, there would still be some particles in there that would still have more particles than the typical area of solar wind. But these particles are charged, they're energized. So when they hit our atmosphere, they cause a display, as we'll see here shortly. Just over the top of the atmosphere of the sun, we have the corona. The coronavirus, which is happening right now, you may hear. Corona means crown. And so we consider this to be the crown of the sun. You can see it very dramatically when there's a solar eclipse in the solar, so that the moon is going in front of the sun. Then you can sort of see the corona there. The reason why the coronavirus is called what it is that virus structure also seems to have crowns on it along the way. But notice the corona is 1,000,000 K, which means it's 1,000,000 degrees Celsius, give or take a few hundred degrees along the way. That's really hot. But again, it's also very wispy, very light and not dense at all. So this, if I were to sort of take a Lysol spray can and spray stuff out, that would have a lot more density. That would have a lot more stuff than our typical area of corona of the sun. Go below that, we have the chromosphere, which is just at the top of what we would see on the sun. Notice the temperature went down here. 1,000,000 K has 6 zeros, 100,000 has 5, 10,000 has 4. So we're actually decreasing temperature as we go down to the photosphere. And if you look up at the sun, don't look at the sun, but if you look just look for it, but don't look. What you're seeing, if it's not a total eclipse and you're seeing the corona, what you're seeing is the photosphere. That's what photo means, essentially, is that you're seeing the sphere of the sun. That surface is about 6,000 K. So we're talking 10, 11,000 degrees Fahrenheit. Not really that hot. You would think it would be a lot hotter, but that's how hot it is on the sun. Sunspots are a little bit less in terms of the temperature. Now, below what we see when we're sort of looking up at the sun, don't look at the sun, is the convection zone. These are the sort of gas bubbles that are bubbling up, and they're releasing the energy at the top. The heat rises. Then as they release energy, the gases cool and they sink back down. And so it's sort of just like a regular boiling convection bubble thing going on there. Below that, we have a really, really hot area called the radiation zone. And that's where there's just so much energy, nothing is sort of made into simple structures like bubbles. It just energy shooting every which way to try to get out of Dodge. And then at the very center, we have the core. That's where the engine is running. That's where the fusion process, where the hydrogen is being turned into helium. That is all the way up to as much as 15 million K. So we're talking 15 million degrees Celsius. We're talking about 25 to 30 million degrees Fahrenheit. This is a hot, hot, hot area here. We'll talk about all of those zones a little bit more here in a moment. But when we get to the core, we're doing nuclear fusion. Nuclear processes, I talked a little bit about this earlier in the semester, I believe, but can be two different things. We can talk about fission, which is taking a big piece and splitting it apart. Usually we use something like uranium or plutonium to do that. So we've got a big particle here like uranium-235 or 238. That refers to how many particles are inside of this atom. And then it splits. And when it splits, E equals mc squared. Some of that matter is converted into energy. But fusion is a simpler process to sort of conceptualize here. We start with two particles, individual particles in our sun of hydrogen, and they fuse together and in a multi-step process turn into helium. Well, that also, E equals mc squared, generates energy with a tiny bit of matter along the way. Most of the time, a hydrogen particle and a hydrogen particle will stay away from each other. They are protons. They're the center of the hydrogen atom, and they have positive charges. And in nature, in charges, like repels, opposites attract. So they have to be under really high pressure, which happens in the center of the sun, all that matter pushing in, and very high temperatures, which means they're buzzing around really, really fast. They slam together. When they slam together, that's fusion. That's the fusion process. And what's happening in the sun is we have so many things happening that they'll turn into duos, dyads, and trios, triads, and then finally into stable helium atoms, which we call the proton-proton chain. What we'll have is our hydrogen atoms slamming together into the little dyads, the duos, the two pieces here. Then those, of course, will continue to, as a duo, spin around at high temperatures under high pressure, and they'll fuse together with yet another proton. And then these trios, these triads here, will also be spinning around at high temperatures and under high pressure. And they will slam together and form a stable quad. They will form 2 protons, 2 neutrons. Notice we start out with 4 protons. We end up with 4 particles. but 2 of them have turned into neutrons here, which means they've lost their charge. Well, at each step in this process, as things are slamming together, they're generating different types of energy as well. So we start out with 4, we end up with 4, but a tiny, tiny bit, but less than 1% of the matter that we started with is converted into energy. So more than 99% is still here. And this is that ash I was talking about before. We start out with hydrogen, we end up with helium. And we see that process in our star, the sun, as well as a bunch of other stars that we can take readings from. So the total mass, as I mentioned, is less than 1% lower when we end up here. So the sun is losing a tiny bit of mass over time. Eventually the helium will build up, and in really, really, really big stars, helium can then fuse into bigger elements and bigger elements. Most of the elements that we have in our body, in our world in which we live, oxygen and carbon and other kinds of things, were created inside of stars, but they have to be bigger stars than our sun. Our sun won't really end up having enough energy and pressure, enough mass left over to create this, to turn helium into higher elements for any length of time. As the fusion creates this helium and creates this stuff that's happening in there, it will push out more if the temperature rises, if it's generating more energy. As it pushes out more, the sun expands just a little bit. It doesn't expand huge amounts. We don't have a pulsing or variable star really. It's very, very minor. But as the core expands within the sun, it begins to cool. As it begins to cool, then what happens is gravity takes over a little bit more and it pulls it back in. And as it pulls it back in, it begins to slam things together at a higher rate, and then things heat up and expand. So we have this expansion, contraction going on, which tends to keep our sun regulated. We have only a tiny, tiny amount of solar brightening, of solar heating along the way. Now, the particles that are coming off of the core are just trying to get out, but they are so densely packed inside there. It's like trying to get out of a party where there are way too many people in the room, and you're bumping and bumping and bumping and bumping and bumping into people as you're trying to get to the door because you just need to escape. That's what's happening here. It takes about 8 minutes for light to get from the surface of the sun here to the surface of our planet. So 93 million miles, it takes about 8 minutes. That's that 186,000 miles per second that we were talking about before. What we have going from the center of the sun to the surface, however, which is a much, 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 much smaller distance, it can take 50,000 years, not minutes, not hours, not days, 50,000 years. In fact, there are some textbooks that say 100,000 years. The thing is, what's happening is it starts out at 15 million degrees here in the middle. By the time it gets up here, it's 6,000 degrees. If you started out with $15 million and ended up with $6,000, guess what? You've lost almost all your money. If you start out with 15 million degrees here and you end up at 6,000 degrees here, we'll say it's Celsius here, 15 million Kelvin, 6,000 Kelvin here equals about 15 million degrees Celsius to 6,000 degrees Celsius here. What's happening is it's losing almost all its energy along the way. It's hitting, and every time it bumps into something, it loses energy. And so it's got to bump into a lot of stuff to get down that low. Now, as it gets closer to the surface, however, things aren't as densely packed and things are lower energy. So it begins to form into convective bubbles. This is that convection zone I showed you before. So the hot gases are going to be rising with the energy. And as it releases the energy into this final area that has virtually no gas, so now the energy can just escape and reach us in 8 minutes, the cooler gases are going to be pulled back down by gravity. And we end up with convection bubbles. And when we look at the surface of the sun, this sort of looks like caramel that's melting. I always found this to be fascinating. We can see that there are hot spots. This looks like a little heart here. And we can see there are cooler spots. The cooler spots are where gas is sinking. The bright spots are where the gas is rising and the energy is being released. We can actually do different temperature variation studies on these. These are all called granules. And the whole process of all of this is called granulation. So the hot gases are rising in the middle, the cooler gases are sinking down below. And granules, this is actually an active process that you can watch. If you go to an observatory like Kirkwood Observatory in Bloomington on the IU campus, they have a solar telescope. They have a setup where you can actually watch the bubble. Now, these bubbles can last anywhere from a few hours to maybe a super bubble might last a day or two. But they don't last very long. But we can watch this happening on the surface. And that gives us a clue about what's happening underneath as well as we're doing that. Because we can't land on the sun and drill down. One of the things we also note is that we have sort of darker patches and lighter patches on the sun that will be determined by the temperature, but we also can watch them move across the sun. And we can watch as it's spinning, we get a particular velocity in one direction and a particular velocity in another direction. We can measure that with our good old Doppler effect. Remember, things that are coming towards you are blue shifted, things that are going away from you are red shifted along the way. So we can learn a lot by watching what's happening on the sun, the vibrations, by watching things that are coming off of the sun, including neutrinos, we'll talk about that in a minute, and also knowing how things operate under pressure and in high temperatures, and particularly how hydrogen operates. And we can work with hydrogen here on the surface of our planet. Now, one of the things that happens, of course, is as the sun is moving around, part of it's going to be moving away from us, part of it's going to be moving towards us, but we also have different things that are happening with those granules and the things that we can see on the surface, and we can see the vibrations that are happening. The sun is a very active place. We can measure out in terms of mathematics what would happen with temperatures, what would happen with densities, and what we're seeing in terms of what's coming off of the sun matches what our mathematics tell us. I'm not going to make you do the math, don't worry. I'm not going to throw the equations at you, but this has been studied for quite some time. Again, about 100 years is the operative amount of time, because once we got E equals mc squared, once people were figuring out what fusion and fission were, we figured out that's what's happening inside the sun. And you know, that's when we were off to the races to figure out what was happening there along the way. Neutrinos are in fact one of these particles of energy that, and I say particle, and that's almost a misnomer because it's almost not there. Right now, as you sit here watching me, 50,000 neutrinos are going through your nose. 50,000 neutrinos are going through your eyeballs. 50,000 neutrinos, and it doesn't matter whether you're on the side of the sun. See, it's daytime right now. That's why I'm sort of lit on one side and not on the other, because the window is letting the sunlight in. But even if you're on the opposite side of the planet, let's say this is our planet here, and say the sun is over here. You can see it in my picture here. So that means the Earth is going to be over here. The neutrinos will come off the sun and go through the planet and then through your body on the other side. Neutrinos almost never hit anything, almost never interact with anything. You can think about them as X-rays on steroids. They just go all the way through and they don't stop for anything along the way. It takes massive, massive trickery to catch some of the neutrinos. Here's a neutrino detector. Notice the people that are standing here, how large this device has to be just to catch a couple of them. We often have to put them deep, deep, deep underground so that it's shielded from every other possible type of radiation, so that we don't get X-rays and we don't get gamma rays and other things along the way. But when we were trying to figure out how the sun was operating mathematically, it kept telling us, well, you're missing a bunch of stuff. You're missing all these neutrinos here. But as we've gotten better at measuring those things, things begin to fall into line. One of the great, great leaders in this, I wanted to highlight this. This is not in your textbook, so this is extra, extra. Read all about it. Her name was Cecilia Payne, and eventually she got married, so she became Cecilia Payne Gaposchkin. Gaposchkin was another scientist at the time. In 1925, notice that she was 25 years old, which is an extraordinary young age for doing a doctoral thesis. She's one of the ones who helped us figure out the mathematics for all of this stuff along the way. She worked at Harvard from 1938 until 1956. And she reminds me a lot of a woman who was part of my particular upbringing, because notice, I mean, she was there for 20 years before they gave her a legitimate appointment along the way. There is gender bias. There are lots of biases, even in the supposedly unbiased discipline of science. The person I was referring to, and I may have mentioned her in an earlier lecture, but if I didn't, I want to make sure I do, and forgive me if I go off on a little bit of a story. I had a teacher named Mrs. Griffith, and she was my math teacher for 3 years while I was in what counts for high school. She was my algebra teacher, my geometry teacher, my trigonometry, analytic geometry, college algebra, and calculus teacher. She had 2 master's degrees in mathematics. She had one in pure math, which means you're just doing math, you don't care if it applies to anything. And she had a master's degree in applied math, which meant engineering and physics and chemistry and other kinds of things. How many of you have ever taken 15 credit hours in one semester? That's actually a pretty good load. Now think about that. Now think about taking 18 credit hours in one semester. That's going to be 6 classes generally. That's a lot. Now think about taking 21 credit hours in one semester. That's 7 classes. That's an overload. Now think about this. Take 21 credit hours of math courses in one semester at the graduate level, no less. Now, my teacher, Mrs. Griffith, went to her dean and said, I want to take these courses. And he said, well, I'll approve your taking these courses as long as you're not working part-time. And she crossed her fingers, put them behind her back, and said, I'm not working part-time. And she wasn't. She was working full-time. She had a job 50 hours a week working for the phone company, where she would basically sit. I mean, we talk about being tired out from sitting in front of Zoom and stuff like that. She would literally sit there for 50 hours a week with a little headset on, connecting wires. These are the days where if you called up the phone company and wanted to make a long distance call, some operator actually had to physically plug things in to connect the wires. She was one of the ones who did that. She sat there 50 hours a week doing this with math books on her lap, doing this stuff. That's phenomenal. I couldn't do that. I could not do that. I couldn't even begin to think about doing that. Now, the reason why I bring her up is because she had 2 degrees in math. Remember, math, pure math and applied math. She wanted to get a doctorate, and her dean told her no, because women don't get doctorates in math. I wonder if she knew about Cecilia Payne Gaposchkin. She probably did. But Mrs. Griffith was probably one of the better mathematicians in the 20th century, and she was told no simply because she was a woman. Don't let anyone tell you no. Don't let anyone tell you that you can't do something that you know full well you can do. Because we owe a lot to people like her, and we owe a lot to people like Cecilia Payne Gaposchkin here. We would not have anywhere near our understanding of the sun without her work. And what understanding we have. This is a dramatic image. I mean, we think about the sun as just sort of there. It's a fiery place. This almost looks like Dante's Inferno when we're looking at it. The sun has quite a lot of weather activity going on with sunspots and flares, which are explosions, and prominences, which are eruptions on the surface. We even get into what are called coronal mass ejections. All of these are related to the magnetic fields, and you have to know that the sun is really powerful if it will take something like hydrogen. You've all played with magnets before. If you play with magnets, what do they all have in common? They're all metal. iron and stuff like that. It has to be really, really powerful to take something that's not magnetic. I mean, imagine if plastic were magnetic. Imagine if paper was magnetic. Imagine if things like that. Hydrogen is not magnetic, and yet it can turn it into, there's so much energy, it can turn this into a magnetic field area. This picture is also not in your textbook. I brought it from another spot because, no pun intended there, because when you're looking at it in black and white, you see some features, or some features are brought out that are a little less prominent in the color one. Again, you have all of your granules here. Notice how dark this is, and all of these sort of lined areas. This dark area here is 1 to 2,000 degrees cooler than the surface of the sun. So 4,000 to maybe 5,000 degrees. The reason why it looks dark is because if I were to take that sunspot stuff and hold it up here in my hand, for one thing, my hand would instantly incinerate. But also it would be the brightest thing you've ever seen in your life. And the reason why it looks dark here is because the stuff around it is brighter. But if you look at this stuff, this is where the magnetic field is interacting with the material in the sun. And if you've ever played with the things that you can pick up at truck stops, they sort of have a face, and they have the iron filings, and they have a little magnet. You can put the beard on the guy, or you can put hair on the guy. This always reminds me of that because it's magnetic. The center of this, the completely dark area here, and it's not completely dark. If you were to close in on it, you'd see some stuff happening in there. But we call that the umbra, sort of like an eclipse. The darkest area is called the umbra. The shaded area around it is called the penumbra. And then, of course, out here we have the regular granules that are operating here. The reason why we know this is magnetic is when we look at the spectrum that's coming off the sun. We've got those little spectral lines. Remember, we've got the hydrogen lines and we've got the helium lines. We can sometimes see what's called the Zeeman effect, where we have the magnetic field, the line is going through it, pulling the line apart in 3 different ways. When we got that trident kind of effect here, what's happening is the particles that are following the magnetic line are sort of going in one direction or the other, north, south, and some are still going up the middle. So this is how we can tell it's magnetic. Now, these being magnetic, just like a magnet, we have north and south poles. On magnets, we have north and south sunspots, and they will draw material through them, and we'll get these really interesting effects with material and energy that are on the surface along the way. Now, we can watch sunspots going across the face of the sun, and this is one of the ways in which we know the sun is rotating. It's another way in which we know the sun is not flat Apollo's chariot wheel, but it's 3-dimensional. I talked about limb darkening, L-I-M-B, your limbs. The further out you are from the center, the darker the sun will get on the edges along the way. That's another way in which we know that the sun is 3-dimensional. But as we can sort of watch this go from day to day to day to day. The sun rotates in roughly a month. And again, the size of the Earth here is put up for comparison. So you can see sunspots are massively larger than the Earth. Now, when we look at these sunspots, sometimes they will charge up and have a burst of activity. Sometimes they will explode in X-rays. Sometimes they will explode in charged particles that stream off towards us. When you're up in the International Space Station, if you ever get a chance to go into something like that, they'll probably have some reinforced rooms. So if there are extra X-rays coming off the sun, you can go and stick around in that until the X-rays are gone. Because just like you go to the dentist office, they put on the vest and all of that sort of stuff to keep you safe. There are a lot of X-rays out in space. So if we're sending people to Mars, for example, one of the things we will want to do is to make sure to have some shielding so the people in the probe for months and months to get there are not going to be overdosed with X-rays along the way. But then sometimes we have material that will loop out. Again, we can sort of see a small loop here. We can see a larger loop here. Those are also typically attached to sunspots, not 100% of the time, but most of the time, we will find this happening here. The charge particles are following the loop. The energy and the material from the sun is following the loop, but also gravity will work to pull things back down. Just like if I throw something up on Earth, gravity will pull things down. If I launch a rocket, if I don't give it enough oomph, gravity will pull it back down. That's the same on the sun as well. This would be called a prominence. And sometimes if you look at the sun, don't look at the sun, but if you look at the sun through a solar telescope with a solar filter on it, you can see on the edges of the sun these. Now these will happen, of course, everywhere on the sun, but we can see them when they're on the edges. Then sometimes if we look at it through other lenses, so if we look at it in X-rays or gamma rays or ultraviolet or infrared, we can see different areas of activity. The sun does generate quite a lot of X-rays, especially in active sunspot times here. And we can see swirls of energy and lots of energy off to the side as well. So these would be prominences and flares. Then sometimes we'll have these huge burps of energy and matter, and they will often push stuff out fast enough with enough energy that the sun's gravity won't pull it all back down, and that's where we get extra charged particles. We call that a coronal mass ejection, and sometimes they can look quite huge, but usually it's sort of more like a soap bubble than a sort of brick falling off the sun. So it's very light and fluffy, but it still adds up to a lot of material. When that streams out through the solar system, it is very stormy. But of course, as it's going further and further out from the sun, it dissipates more and more. Here we can sort of see what we call the transition area. We've got the corona at the top, we've got the photosphere down here at the bottom, and we've got this sort of stormy area where we can sort of see the energy sort of coming straight up off of the granules. Then as it dissipates, we end up with the swirls, and we end up with the prominences, and we end up with the solar flares. So we've got quite a lot of activity on the sun. As it gets further and further out, of course, it dissipates, it goes further and further out. It will hit the planets, but by the time it reaches us, it's very, very wispy, very, very sort of very fine kind of sandpapery effect, but it's hitting our magnetic field. And as it hits our magnetic field, we get these wonderful aurora patterns. Sometimes we have more, sometimes we have less, because the sun is sometimes generating more particles, sometimes less. If we get a really strong burp that hits the planet, it can have enough extra particles to go in to affect, say, satellite communications or cell phone reception. In the early days of cell phones, most of you are probably not old enough to remember this, but I am. They would actually announce on the radio whether it was a good day or a bad day for your cell phone, because cell phones didn't have really good antenna, and the antenna could be disrupted by solar activity very, very easily. To this day, AM radio can be disrupted by solar activity. If you look at AM radio stations, for example, they will often be putting out things at 100 times more intensity during the day than during the night. Try this experiment at home sometime, in fact. Play with your AM radio. If you have a radio at home, play with your AM radio. Go out at noon. And if you're in Indianapolis or in Bloomington or something like that, look for your AM radio stations in your city. And then look for AM radio stations, go online and look for AM stations that are about like 100 miles away. If I'm here in Bloomington, I can turn my radio on to AM 1370. As I drive up to Indianapolis, by the time I'm up to Greenwood or something like that coming up from Bloomington, I can't get that station anymore during the daytime, because there's too much solar activity. Now, at night, when I'm coming back home, say I went out to dinner with a friend to a movie, or I used to go to school at night up near Butler University, and I would come home, I could get the radio station the whole way. I could get 1370 the whole way. That's because there's no solar activity on the other side of the planet disrupting the broadcast. The weird thing is, the radio station itself is putting out 100 times less energy and it's still reaching me. So this is the other part of your experiment. Try to get to those radio stations that are 100 miles away during the daytime. Now go around midnight, say sort of the midnight's the best time because we're directly opposite the sun. But look for AM radio stations, say 1,000 miles away. If you're here in Indiana, look for AM radio stations, go online and look for AM radio stations, say from Atlanta or from Kansas City or from Detroit. I'll bet you can get them. They're not gonna be great, but you can pick those radio stations up because the sun's particles aren't hitting on that side to disrupt. Now, I love a good aurora. As I've mentioned a couple of different times in this class, I'm sure, because I do it a lot. I go to Iceland 3 or 4 times a year. This year, I'm sort of missing it because we're not being able to travel. If you're watching this video anytime during the time that I'm filming, we're in the midst of the corona virus pandemic here, so I can't travel. But I typically will travel 3 times during the fall, winter, and spring. I hardly ever go in the summer. During Iceland because you can't see anything in the sky in the summer. The 24-hour sun, or at least the effect of the sun. The sun goes down a little bit, but the light still pokes over the horizon, so you don't get much in the summer. But if you go in this fall, spring, or winter, you can get scenes like this. And this is what happens. The green is the aurora. The purple is another phenomenon that, I kid you not, is called Steve. Look it up, it's rather fun. But you can get these kinds of effects on the Upper Peninsula of Michigan on a regular basis, in Maine and New Hampshire, upper state Washington and Idaho and Montana. You can often get these too. Go up to Alaska, you'll see this. I hope you get the chance to see the aurora sometime in your lifetime. It is a truly magical and mystical kind of experience, but it's also the sun interacting with our atmosphere. Now, sunspots come and go. Sunspots come and go in basically an 11-year cycle, and they are sometimes more intense. See, notice here around 1960, we had really intense times. Notice here around 1900 to 1910, we had a lower intensity. They're mostly around the equator, and because they are magnetic, they often will have 2, a north and a south pole. That go, and so they'll spread out and then collapse and spread out and collapse. And as that happens, we can sort of see them going up and down. Now, we've only been watching sunspots for about 400 years. Why is that? Because don't look at the sun, as I mentioned before. If you try to look at the sun, it burns your eyes out pretty quickly. You're not going to see sunspots typically just looking at the sun. Because the power of the rest of the sun blots them out. So we had to wait for telescopes. It is one of the sort of pieces of history of science that Galileo burned out his eyes looking at the sun through the telescope. He mostly didn't, and he sort of figured out rather quickly this is a bad thing to do. Telescopes today have warning labels on them. Don't look at the sun through this. Along the way, so he didn't like stare for hours and hours at the sun through a telescope and burn out his eyes, but he did get a little bit of damage in trying the occasional experiment. But nobody saw sunspots until we could look at the sun through a telescope and magnify it. The way you generally do it is you send the sunlight through the telescope and project it onto the wall or something like that so you can watch, and then you can see the sunspots. People in China had recorded sunspots before, but they thought they were clouds in front of the sun. And that's a fairly good idea along the way. So they had, again, done that projector kind of thing, which you can do during an eclipse as well. You can like have the light come through a pinhole and it will project an image on the side. So we only have about 400 years of consistent data looking at sunspots. Now, one of the things that happened, Galileo started looking through telescopes in 1609, 1610, is shortly after that, we stopped, it seemed, having sunspots. for about 60 years or so. This is called the Maunder minimum here. And then it sort of generated up again with a few dips. Here's the question scientists have. Is this normal? Is having sunspots on a regular basis normal and this low period here abnormal? Or is this high activity period abnormal and this is normal? So we could go for, say, 1,000 years with sunspots and then have 10,000 years with none. Or we could have sunspots for 10,000 years with the occasional 10, 20, 30-year blip of no sunspots. The answer is we don't know. We don't know. We haven't been watching them long enough. So we're still trying to figure out the variation pattern. But what we do know is when we're watching sunspots, they come and go as a collective in roughly 11 years. And partly that is because the sun, not being solid as it's spinning around, is actually spinning around differentially. And the equator is spinning around faster than the poles. So as I mentioned before, the sun goes around in about a month's time. The poles go around in about 30 days, whereas the equator goes around in about 25. And as that happens, notice the lines, the magnetic field lines that are straight up and down, just like on our planet, north magnetic poles at north and south magnetic poles at south. Actually, it's opposite that, but you get what I mean. We are, in fact, spinning, but we're solid. If we were spinning and not solid, these lines would get twisted so that after a few years, they're mostly horizontal. And when they're mostly horizontal, that's when the sunspots keep forming. But as it continues to spin, they spin and spin and spin out so that at the end of 11 years, they're back to being vertical again. So they go vertical to horizontal to vertical in 11 years. But when it ends up at the next vertical stage, this over here will have the south pole at the top and the north pole at the bottom. Now that's magnetic pole, not the physical pole. So the magnetic lines will twist. And here we can see one of the last complete sunspot cycles. I don't have a picture of this for our latest one because we're just ending one now as well. Notice in 1996 to 97, not a lot of sunspots, but starting in 98 and going up to 2001, 2002, huge amounts of sunspots, but then the magnetic lines become untwisted again. So by 2006, we're back to very low light activity along the way. So these are taken from the SOHO satellite, which is a solar satellite that's put up there and keeps constant monitoring on the sun. We have a new picture pattern that should be coming out. We were delayed in our latest pattern here. We went for a couple of extra years without any sunspot activity, and people wondered, are we entering another minimum period? But then they erupted again, which is why we don't have a complete one of these yet for that, because they're just now putting it together. But as we look at sunspot activity and the temperature on our planet, we can sort of see that there is a little bit of correlation. One of the things that we see, however, is that the amount of sunlight that we're getting here on the planet is pretty consistent over time. In fact, reaching into sort of 2020, it looks like we're getting a little bit less. And our temperature is still edging upwards along the way. So sunspots can have an effect. We're not entirely sure what that effect is going to be. Here, I'm going to take us back to this. This area here is called the Maunder minimum. We had what was called the medieval ice age. We had the medieval warming period, which was before all of this. So we're talking back, say, maybe to the 800s, 900s, 1000, all the way up to maybe 1400, which is when the Vikings made it all the way across the sea, because there wasn't nearly as much ice. They made it to Iceland, they made it to Greenland, they made it to Canada. But then as things began to cool again, they couldn't make it across anymore. They abandoned Canada and they abandoned Greenland because they just couldn't make it there anymore. It's a wonder that they didn't abandon Iceland as well. But we entered what was called the Little Ice Age, and you can do some research on the Little Ice Age. That may correspond to some extent to what was happening on the sun with the Maunder minimum, but we don't know enough about the mechanism between sunspots, excuse me, sunspots and the climate change. But as I mentioned before, when we were talking about things geologically and atmospherically, our climate changes due to a lot of different factors. One of which is the amount of particulates in the sky, so that we put in as part of pollution. So we should be diligent at paying attention to these different things. Then this is one last thing. I want to leave you with one last thing for our class. This also comes from another textbook, so it's not in your textbook, but the sun is putting out energy and gravity is pulling things in. That's keeping our sun in balance. But beyond that, we still have gravity outside of the surface of the sun. That's why our planet goes around. That's why all the planets go around. That's why the comets that are out there in the Oort cloud stay along. Well, the sun pushes out with its solar energy and gravity pulls in. That balancing area where the energy is pushing out but the gravity is pulling in, we can call the heliosphere. We've got this bubble around us that helps protect us. Our sun is going around the galaxy roughly once every 250 million years. If you think back to one of our very early lectures, I think it was lecture 2 or 3, maybe even lecture 1. I think in this class it was lecture 1. How fast are we going? As we're going around the galaxy, we have this bubble, almost like a Star Trek shields up kind of thing, called the heliosphere. And it's bumping into the other gas and dust that's out there in the galaxy. So we have this area called the heliopause. So as we're going around, and we're not just going around, we're going sort of up and down and up and down and up and down, sort of like a warped record. If you've ever seen a vinyl record that's been left out in the sun, it goes in a wavy pattern. So we're going up and down through this gas and dust, and we're pushing it away. Now, when we launched the Voyager probes, we sent Voyager 1 to Jupiter and Saturn. We sent Voyager 2 to Jupiter, Saturn, Uranus, and Neptune. But one of the things we planned for both of those is after Jupiter 1, or Voyager 1 went to Jupiter and Saturn, it started going out of the solar system. After Voyager 2 went by Jupiter, Saturn, Uranus, and Neptune, it started going out of the solar system as well, in a different direction. But they're both going out towards the heliopause. This whole area here is called the heliopause. And they have both reached the point where, as they're reaching further and further out into space, they're beginning to get more of this kind of gas than they are this kind of gas. When you're getting more interstellar gas than solar gas, you have reached the edge, one of the definitions of the edge of our solar system, and have gone out into interstellar space. So we actually have 2 probes that are still talking to us that have gotten to that point. There are 2 other probes, 2 Pioneer probes, that have probably also reached that point, but they're not talking to us anymore. Their batteries have run down. Now, one of the important things about this is that as we're going through, this heliosphere is keeping us safe from a lot of things. If we might be bumping into things, but they're bumping off our shield. Every now and then, however, we might have something that's not just sort of coming at this and then gets deflected, or coming like this and gets deflected. We might have something that's coming in at an angle like this, and it might do something like this. We had this happen just a few years ago. It was called Umeomea, or Oumuamua, sorry, I mispronounced that, Oumuamua, yes. Muamua is a Hawaiian island, or a Hawaiian word, because it was discovered by the observatories on the island of Hawaii. Muamua was our first confirmed interstellar visitor from outside. It may have been a comet, it may have been an asteroid. There's still a debate about what it was, because it was coming in at an odd angle. It was going very fast, so it just sort of bent around the gravity of the sun a little bit, but then continued on its way out. As it's coming in like this, we didn't actually pick it up until it was about here and already on its way out. But because of that, we were able to traject from where it had come from and to where it's going. And it's too small and too dim to really continue to track now, so we can't pick it up on our telescopes too much now. But for a brief time there, we were able to take different kinds of readings from stuff that's outside. We've since found a couple of other things, one of which has gone through and one of which came in and got trapped. So if we get things at odd angles, we can still see visitors from outside, but our sun's heliosphere protects us from most of the stuff that's going to hit us edge on. And that once again helps reinforce the idea that our inner solar system, where our planet Earth is protected by multiple forces. And I think that's a wonderful note on which to end. Now, if you want to learn more about the interstellar gas out here, if you want to learn more about these stars, if you want to learn more about galaxies of stars that are way beyond our solar system, sign up for 102. That's what we study there. But otherwise, we will conclude that by again reminding you, don't look at the sun. So I could sort of turn my head towards the sun and it's like, nope, not gonna look at it there. But I appreciate your being part of the class. I appreciate your trekking through astronomy during this period of onlinedness where we are doing things in a virtual setting. And I thank you for getting all of your assignments and work in. Again, if you need to Zoom with me, let me know. And otherwise, I hope you have a good rest of the semester and a good rest of your college career.